right, so here we are. Did anyone here forget about daylight savings time? No, it's already been a day, but yeah, that could have happened because obviously, it just sneaks up on you. It used to start in April. Now all of a sudden it's early March, and I guess it'll last until October sometime, or maybe early November. But that first week, it's tough because we have to get up extra early. But it looks like we all made it, and that's good. So what do we have to do today? Well, first of all, I hope everybody is working on their midterms because I want them by tonight at midnight. And I see a lot of you have been sending them to my purchase account. That's very nice. Thank you. And I will gather them up and grade them later in the week or possibly over the weekend. So in the meantime, we can focus all of our attention on the new material, which we just started last time, which is chapter 8, our discussion about interest rates. So anyway, let's just quickly review what we were doing. So we started out by talking about simple interest. And so simple interest, let me just make a note here. Simple interest is simply interest that's paid on the principal amount that's been borrowed. Okay, so for every loan, every time somebody borrows money, every time somebody lends money, the amount involved is called the principal. And the interest that's calculated entirely on the principal is referred to as simple interest. Now, there's another kind of interest that we'll be looking at today, which is more complicated, but the simple interest is simply what percentage of the total are we paying every year in interest or receiving if we're the lenders. All right, now it turns out that there's a formula for calculating this, which is very straightforward. And let's see, first let's remind ourselves what variables we've introduced. P is for principal, of course. This is a dollar amount. R is the rate of interest, and this is a percentage of the total of the principal. So we always express that as a percentage or a decimal. Okay, so for example, if the rate of interest is 5%, we'll write that in our formulas as 0.05. All right, we should not use these because they're going to give you the wrong answer. It looks nice the way it's written here, but in a formula, we use decimals in a formula. It should be on Moodle. Let me just go look. Isn't it there? Let me go look and see, just in case something went wrong. I will double check right now. We are yeah, there it is. It's labeled MT1 for midterm 1. Okay, so it's right there. All right. Yes, and everything else is here. I've been pretty careful about posting everything as soon as we're finished with it. I don't believe anything is missing, including our videos. If you want to watch one of these videos again, they're all right down here. This is just a link, so you can click it on. It'll take you right to the YouTube video. And our videos, as you know, in case you want to rewatch any of them, are hiding in my YouTube account because apparently Zoom is not really set up to store a large number of videos. And so I was told that the best strategy would be to put them in YouTube, and that's exactly what I did. It's under a playlist. Okay, we have all these different playlists, and ours, of course, is right here. So this would be that's one of them. So the list is over here. They're all posted, and so you can watch them anytime you want. And if you really feel ambitious, they have, I don't think anybody's ever actually done this, but they have these little thumbs ups and thumbs downs where you can actually vote, I like this video or I don't like it. Okay. So yeah, you can feel free to do that if you want to, but that's all right. All right, anyway, so let's get back to this. So in addition, we need time, and time, I want to point out, is measured in years. And the reason why that is so important is because if you have a formula or you have a fraction of a year, for example, 6 months would be, If you have, let's say, a 6-month period, then time would be 0.5 for 0.5 years. So in other words, you don't express this as 6 months, you express it as 0.5 years. And also I want to point out the word term is appropriate here as well. The word term is often used to represent the time frame over which money has been borrowed or lent. Now, here's the first one that's a little strange. This notion of future value is very important because it helps us understand if we invest money, how much will it be worth in the future? For some reason, the book chooses to call it A, so we'll just have to get used to it. I don't know why, but they're calling it A, and that means how much will a sum be worth in the future if we invest it or lend it today? That's often a question that we need to answer if we are saving, especially for long periods of time. We want to know how much we'll have in the future so we can plan, for example, for buying a car, buying a house, or for possibly retirement. And then interest. Now, this interest is different from the R back here. This is an interest rate. This is a dollar amount. So we have to be careful with this one. I is measured in dollars. Okay, R is measured as a percent. I is measured in dollars. Very good. All right, now once those are, we've established those, there's a few formulas that we need to know. For example, it turns out that the formula for calculating simple interest is very straightforward. I simply equals P times R times T, principal times rate times time. And so this is our dollar amount that we'll earn. If we start with P dollars, we earn the rate of interest TR, and then T is the number of years for which we leave the money on in our bank account, let's say. All right, so we ran through several quick examples of this, and we found that the formulas are indeed very straightforward, as long as we remember that R is a percentage, okay? T is in years. So what examples did we do? But here's a good one. We start with $1,000. We leave it in the bank for 1 year, and the account pays an interest rate of 3% per year. So right away, we know that P is 1,000. R is 3%, and T is 1 for 1 year. Okay, so now you can just directly plug those in. Here's your 1,000. Here's your, that's your P, that's your R, and this is T. And when you multiply those out, you'll see that you've earned $30 worth of simple interest during that year. All right, and it's really that straightforward. All right, now, we also did a few other examples just to get some practice with this concept. For example, we did here. We noted that while we're earning $30 worth of interest in this account, when the year is over, the total balance in our account will actually be $1,030. So while I equals 30, we still have our principal of $1,000. So that means the total balance in our account equals P plus I equals $1,030. Now, this number is what we mean by future value. And of course, all that means is that if we started with $1,000, that means in a year we'll have 1,030. So the 1,030 is called the future value of $1,000, the starting amount. All right, and you can see here then that we formally defined our formula for a future value right here. And that equals principal plus simple interest in this case. Now, algebraically though, because I equals PRT, if you plug this into this formula, you'll see that you actually have A equals P plus PRT. And now I can factor out this P. And I end up with this expression. So both of these mean the same thing. Depending on the circumstances, one of them might be easier than the other, but they both represent the same information. They're basically simply telling us that at the end of the year, our future value will be the original principal plus whatever we've earned in our account during that time in interest. Okay. So anyway, yes, so we can see how this works now, but this, keep in mind, this is all with simple interest. When we introduce the other type of interest, which is called compound interest, then the formulas will become much more involved. They'll be more complicated, and so we have to get some practice with them. Lots of practice. Okay, because, they're a little, the problem with these formulas that we're going to see later on are that they involve a lot of parentheses. And whenever there's parentheses involved, well, let's just say the potential for mistakes is very, very high. So don't worry, we'll do this very carefully. But so in the next slide, you can see that this is exactly what we just saw earlier, that the future value is equal to 1030. All right, and of course that comes from our principal and our interest. Now, if we did it the other way, if we use the other formula, you can see what we've got is we start with 1,000 and we multiply that by 1 plus the interest rate and the time, and we end up with exactly the same result as you can expect. So either way, we'll end up with the same result. Now, I do want to show you, we've already seen this, but it was a quick example where we had a time frame that was less than a year, just to see how that changes the way we calculate this. For example, what if we had a situation like this? An investor deposits $1,000 for 6 months. All right, so that means we have P is 1,000. And the key here is that T is now, what did I do? T is a half of a year. Think of it as 6 out of 12 years, which you can reduce to a half a year. And then the interest rate is 4%. And so let's plug in our numbers. Here's P, here's R, and here's T. And when you multiply those out, you get $20. That's our simple interest earned over 6 months. Now, the reason why all this is necessary is because the interest rate, this is an important detail, the interest rate is expressed on an annual basis. So that's why it's necessary to adjust it. The purpose of this T here is to adjust our interest rate to the time frame over which we are borrowing or lending this money. Our 4% itself means per year. So if we're leaving the money in the account for only 6 months, then we have to adjust the formula and reduce it to, in this case, a half, because we're not earning $40, are we? We're not leaving the money there for a full year. Instead, because the money is only staying for 6 months, we're only getting $20. All right, so the others are pretty straightforward, but so we just have to watch it with the time. Now, if we left the money there for 2 years, on the other hand, let's just quickly throw that example in here. If instead, if the investor deposits $1,000 for 2 years in a bank that pays 4% per year, the simple interest will be of course, then it's I equals PRT, which means 1,000 times 0.04, but now the T becomes 2. And so you end up with $80, okay? And again, it's all to the T 2 years instead of 1 year or 6 months. And then, just as a quick reminder, then the future value would be P plus I is 1,000 plus 80 is 1,080, or else you could use this version of the formula. All right, so you still end up with the same amount, of course. Whoops, let's move this over here. All right, so that's how it would work in the opposite case where the time frame is more than a year. You literally just put the number of years there for T. And so it stands to reason that if we're making $40 in simple interest in 1 year, it should be $80 in 2 years. All right, now, what we did next was we saw that our original formula, I equals PRT, can be rearranged algebraically to solve for any variable in this equation. In other words, we can solve for not just I, which is enough. I mean, it's a great little formula here, but we can solve for I, P, R, or T. All we have to do is rearrange it algebraically. So if you started with I equals PRT, and I need to know P, I'll divide both sides by RT. And then we'll end up here. That's how we do this. So in other words, you can actually get 4 different variables out of the same equation by rearranging it algebraically. Okay, so we saw a few examples of this. For example, here we had a case where a homeowner borrowed from a bank. We know that I is 20,000. The rate is 4. And the principal will be repaid in 5 years. So based on the formula we just had a second ago, P equals I over RT. When we plug in these numbers, and being very careful, by the way, on your calculator, what you have to do is put 20,000 divided by, and then in parentheses, 0.04 times 5, close equals. So in other words, in the denominator, in spite of the way it's written, you do need to have parentheses surrounding this entire denominator in order for this to work in your calculator. And when you do it properly, you'll see that, of course, you end up with $100,000. They would have had to have borrowed $100,000 in order to pay $20,000 worth of simple interest over those 5 years. Okay, so always be careful with those parentheses when you're using your calculator. Right? If you left them out, you'll definitely get the wrong answer. All right, now how about the second case where we solve for the rate of interest? Can we do that too? Of course. We go back to the original equation. Oh, yes, so $100,000. Make sure you can get that as well. All right, if not, the most likely reason is because of the parentheses. Okay, I assume you all have that calculator in front of you. Yes, you do. If you have your cell phone there, you have a calculator, which is what's so nice about this. And of course, as always, make sure it's on the scientific calculator mode, and you should be good. All right. Now, how about this next case, computing the interest rate? So once again, we took the original formula, and we need to know the interest rate. And so what I'm going to do is divide out the variables that I don't need, which is P and T. And that would be, there you go. There's our formula. Let's check out an example. Now remember, this one, you're going to end up with a fraction or decimal when you're done. So for example, here, an investor puts $1 million into a CD for 1 year. So T is 1 year. And the interest is 20,000. So the question is, what is R? All right. So we come back to the formula. So remember, P is 1 million. I, the simple interest is 20,000. And T is 1 for 1 year. So we plug everything in. And again, on the calculator, you'll have to put 20,000 divided by, open parentheses, 1 million, which is written like this. And it'll come up 0.02, which you know is 2%. All right, how do we go from here to here? If you multiply 0.02 by 100, you'll end up with 2%. All right, so that means in order for this investor to have earned $20,000 in this account, the rate of interest must have been 2%. Beautiful. All right, now there's one more case we did not consider yet, and that's time or term, which means the same thing in this context. So let's go and look at a formula for solving for time. And of course, we start with the same equation. We just rearrange it a little, and we end up with what we're looking for, which is our formula based on time. So we can figure out how many years it takes to achieve a certain result. Okay, and this is also very important information, especially if, like I said before, imagine yourself trying to save for a new car or for a house or something that you want to buy. It's very important to be able to figure out how long it'll take for your savings to grow to the level that they need to be. All right, anyway, so to solve for time, again, we start with our basic equation and divide out all the non-t variables, I guess you'll call them. And so we end up with this. All right, and that's all we need to do to solve for the time. Now remember, this one again is in years. If it turns out to be a fraction, that means that it is less than a year. All right, let's look at this case. We start with $100,000. The rate is 3%. And the simple interest is 30,000. So the question is, how long will it be if this CD matures? Now remember, a CD requires you to keep your money in the bank for a fixed length of time. And it's usually an even number of years. It's not some peculiar amount. It's typically a year or 2 or 5 years. And they can often go out as far as 10 years, but these are typically even numbers of years. So what we need to do is solve for time. Okay. Now, let's set it up. So now, of course, again, we go back to our basic equation. As we've seen before, we have I equals PRT. We can divide out the P and the R rather. And we already know that the interest is $30,000. It's a $100,000 CD. The bank pays 3%. And if you go through all those steps, you should end up with 10 or 10 years. Now, with all this being said, we're now going to introduce a far more important, but also far more complicated type of interest. And this is known as compound interest. This is what we've been saving for the whole weekend. Compound interest refers to interest paid on previously earned interest. So in other words, if you leave your money in the bank long enough, initially you'll only earn interest on the principal, but when you start accumulating interest in your account, the interest that the bank pays you will be based on both the original principal and the interest that you've earned up to that point. So that interest is far more complicated to calculate. And in the beginning, in early years of an investment, it is a fairly small amount compared to the simple interest, but over time, it will grow much more rapidly than the simple interest. So this is exceptionally important for long-term planning, like retirement planning, let's say, because over a long enough period of time, eventually you'll have more compound interest than simple interest. So therefore, the interest that any borrower or lender pays or earns ultimately comes from two sources. First, we have the interest on the principal, which we already know is simple interest. And then finally, interest on interest, which is known as compound interest. Now, what I'd like to do before we dive into this, I'd like to show you a quick example of how this works. Otherwise, it might not make any sense to you at all. So earlier, we had an example where, let's say, we deposit, oh God, an investor deposits $1,000 into a bank account for 1 year that pays a 4% rate of interest. Okay, so now well, first of all, let's figure out the simple interest. We have I equals PRT equals 1,000 times 4% times a year, which is $40, of course. Now, here's the interesting part. And by the way, we can illustrate what we're doing here with a simple type of graph, which is known as a timeline. And so in this case, the timeline would be very simple. We'd start now, this little zero means today. And this little one means 1 year in the future. So we start out with $1,000 today. And in 1 year, we have 1,000 times 1 plus, this is 1 plus 4% times a year, which is 1040. Okay, and in fact, this is the future value. So we start with $1,000 today, and at the end of the year, we have $1,040. Okay, and that's based on our formula. So when the year is over, the bank credits our account with $40. Now, in practice, this is actually a very simplified look at the way interest is calculated. Suppose we had the following scenario. Oh, let me just leave that up there for another minute in case you want to copy it. So these timelines are very, very helpful for helping us figure out how much interest we actually have. All right, so what if we have the following situation though? Suppose the bank announces that instead of paying 4% interest once a year, it will now pay 2% twice a year. The question is, will that have any effect on the amount of money we have in our account at the end of the year? All right, so what we would like to do is illustrate how this affects the amount of money we have and whether it makes us better off or worse off. So now we're going to go back to our timeline, and we're going to do this in an interesting way. We'll start out with our $1,000. Now we need another time step, 0.5, which is 6 months in the future. One is still 1 year. Now remember, the principal is 1,000, and the rate of interest is 4%, and this is a 1-year investment. So the question is, how much will we have in our account at the end of 6 months? So we'll have 1,000 times 1 plus. Now, in 6 months, this time element will only be half a year because this is taking place 6 months in the future. Actually, you know what, let me do this. Just to avoid confusing anyone, the time of this entire investment is 1 year, but we're calculating the interest rate 6 months at a time. So here I want to know how much this is worth in 6 months. And well, you can see that it's just equal to 1,020. Now, here's where it gets interesting. In 1 year, 6 months later, when we go to calculate this, look what happens. The principal is now 1,020 instead of 1,000. Hold on, I'm running out of space. 1 second. So we've got a 4% rate of interest. Again, we're using a time of 0.5 because this is 6 months later. And the key difference here, what I want you to notice is that the P is 1020 not $1,000, because after 6 months, we have $1,020 in the bank, not $1,000. This part hasn't changed. It's still 4% earned over 6 months. So when you multiply this out in your calculator, you might be surprised to see that you get $1,040.40. So what just happened here? We've got 40 cents worth of interest that we did not have before. So the additional 40 cents is known as compound interest. It is based on the $20 worth of interest earned during the first 6 months. All right, so does everyone get it? You see what I've done here? I've applied the future value formula twice, not once at the end of the year. I've split it up into 2 parts, but by doing it that way, all of a sudden at the end of the year, instead of having 1,040, I've got 1,040.40 cents. And so the extra 40 cents that we just got is actually what we mean by compound interest. And the reason why we have it is because during the last 6 months of the year, the interest was applied not to 1,000, but to 1,020, which includes the interest from the first 6 months. So therefore, this makes us happy to see this, that we say to the bank, listen, thank you, you're giving us extra interest. Okay, so now what I'd like to do is stretch this out again, and let's assume this time that instead of paying 4% for the full year or 2% twice a year, we're going to increase it again to 4%, split up 4 ways. In other words, 1% 4 times a year. So we're going to move this up to the next level and say, listen, now the bank is saying, maybe we'll try this. The bank now announces that instead of paying 4% once a year, 1% 4 times per year. Instead of 4% once per year or 2% twice per year. Now, what will this do to the balance in our account at the end of the year? Well, presumably, if splitting up the money, the interest, into 2 pieces added to our balance, this should also increase our balance even further. In other words, when the year is over, we should actually end up with more than $1,040.40. So we're going to prove it right now. And along the way, get a lot of good practice. All right, let's see how much we would have in the bank at the end of the year if we're getting 1% 4 times a year instead of 4% once a year or 2% twice a year. All right, now this one, I'll have to split up into 2 pieces. I'm sure that we're going to run out of space. So we'll start here, and then let's say, maybe I can do it twice, 2 at a time. How about if we draw it 6 months here? No, it's not going to work. We could probably fit it in here. We'll start out today. 1/4 of a year in the future is here. 1/2 of a year is here. So this is 3 months in the future. This is 6 months. This is today. So we have 1,000 here. And now remember, they're paying us 4%. 1%, 4 times a year. So here, so in the formula, if you notice, the product of 0.04 and 0.25 is 1%. So basically, what you're actually doing here is multiplying 1,000 by 1.01, which is $1,010 even. Now, that means that in 6 months, when we go to apply this formula again, we'll have 1,010 times 1 plus 0.04 times 0.25, which is the same thing as 1,010 times 1.01. And so we'll have 1,020.10 after 6 months. And I guess this could be 3/4 of a year. And this could be a year. Now, by the way, I want to point out that already we're ahead of the previous example, because if you notice, after 6 months, in this case, we only had $1,020. Here we have 1,020.10. So already we're ahead of the game. Now, when we get down here to 6 months, or 9 months rather, we'll have 1,020.10 is multiplied by 1 plus 0.04 times 0.25, which is the same as multiplying 1,020.10 times 1.01, and we'll have 1,030 0.301. All right, and then after 1 year, one plus 0.04 times 0.25. So again, we're basically just multiplying this by 1.01. So finally, when the dust settles, we have 1,040.60, or let's say 604. So after all that work, which we will not have to go through every time, by the way, we have $1,040.60.04 this time. If you recall, in the previous example, we had 40 extra cents here, and in the beginning, with just annual payments, we ended up with just exactly $1,040. So we're not gonna take this any further, although we certainly could. We could break it up into months and whatever we want to do. So what we're going to do is summarize all this onto a single sheet or slide so we can see exactly what's going on here. All right, so let's summarize this. So the way we did this is in all the cases, we had the principal of 1,000, the rate is 4%, and it was a 1-year investment. Now, the frequency of the interest is what we're interested in here. So what I'd like to do is create a little chart here. The future value. Well, first of all, frequency of payments, let's put it that way. And then we'll have the future value. And then we'll have interest. Yeah, I'm trying to, maybe I'll do this by hand because I'm trying to squeeze in a lot of information here. Let's do it this way. We'll put here compounding frequency or frequency of interest. All right, let's do this. I'm trying to figure out how to make this work. There's a lot to put in here. All right, this might work. All right, how about this? I know I'm going to run out of space. Hold on a second. All right, that should do it. God damn this thing. All right, that should do it. It's a little tight, but I can fit it in. So in the first example, interest was paid once a year. And you recall that we ended up with $1,040. So the interest that we earned was $40, all of which was simple interest, which means that none of it was compound interest. Now remember, simple interest, I equals PRT, 1,000 times 0.04 times 1 is 40. Now that never changes. So when we had twice per year, We ended up, if you recall, let's go back and revisit that slide. We ended up with $1,040 and 40 cents, I mean. The total interest was $40.40. Now, the simple interest is always $40 in this example, because right here, what we're looking for here in the compound interest column is the difference between these two. So in other words, any interest that we earn, which is not simple interest, is compound interest. Because remember, when we saw the diagram, where's that coming from? That 40 cents came from the interest we earned during the first 6 months of the year. And then finally, when we did it 4 times per year, in this last example we just finished, we had 1040 and 60.4 cents. So actually, in practice, the bank would round it to cents anyway, but let's just leave it like this. $40.60.4, of which the simple interest is 40, and the rest is the compound interest. All right, so this is all we need to know, because as you can probably guess, if we keep increasing the frequency, let's say we go to monthly, well, what's going to happen is the future value will go up a little further, the total interest will go up, the simple interest will stay the same, and the compound interest will go up. So all but the simple interest will go up whenever we increase the compounding frequency, as it's called. All right, so let's summarize that. Wow, what a complicated chart we have here, but this is extremely important because it helps us visualize what's happening here as we change the frequency with which the bank pays the interest. And you can see that each time they increase the frequency, it's making us better off as consumers. Okay, now, let's just give you a minute to catch up with that. And then I just want to summarize a few key important ideas here. All right, so just a few important ideas here that we want to consider. All right, just one more minute and then I'll have to get going. All right, so what we want to do is try to sort of wrap this up and understand what this is all about. So first things first, as far as the terminology goes, we'll make the following statement here. The number of times per year that interest is paid is known as the compounding frequency. Okay, so for example, once per year equals annual compounding. Twice per year is known as semi-annual compounding. 4 times a year is called quarterly compounding. And then, now normally, of course, in practice, you're not normally going to compound anything like say every 6 weeks or whatever. These are the standard ones, and there's 2 more. We also could find ourselves with 12 times per year is monthly compounding. And then finally, I'll sneak it onto here, 365 times per year, as you can probably guess, is called daily compounding. All right. So those are the standard ones that you might see in practice. You don't find any strange ones like 18 times a year or anything along those lines. These are the normal ones. Now, in practice, interestingly enough, especially if you're putting money in a bank account or borrowing from a bank, the standard in the United States is for daily compounding. So if you go to your bank and ask them how frequently they compound your interest, they'll tell you it's every day. So that's actually good if you're lending your money, but not so good if you're borrowing. That's one of the reasons, by the way, why credit cards are so expensive, because they do the same thing. And if you have a high rate to start with, daily compounding can really, really increase the expense quite a bit. Now, I also want to point out, as you can see from our chart, the following relationship between compounding frequency and interest. As the compounding frequency increases, the total, the principal increases, or future value, I should say, total interest increases, compound interest increases, but simple interest never changes. So in other words, the simple interest doesn't depend on the compounding frequency. It only depends on the rate of interest, the time, and the principal. These others, though, will continue to increase as we keep increasing the compounding frequency. Now, you notice that it took a lot of work to come up with the future value of a sum with, let's say, even with semi-annual compounding. And of course, it took even more work to get it with quarterly compounding. Imagine how long it would have taken if we tried to do this for daily compounding. We would have been here all day. Well, it turns out that we don't need to bother, because there's a formula that we can use to help us with this process. Now, the formula looks very, very complicated and scary when you first see it, but it really isn't. It's just that we need to be very careful, and we have to be extra, extra careful with the parentheses. So what we're going to be introducing here is a formula that's meant to calculate future values when we have frequencies of compounding greater than a year. Okay, so let me just mention this in here too. The formula A equals P1 plus RT only applies for periodic calculation. Well, all right. Let's just put it this way. The formula A equals P times 1 plus RT is not as useful when interest is compounded more than once a year, because we have to keep using it for every period. In other words, you notice how I used it here twice, and you notice how here I use it 4 times. So the more frequently the interest is compounded, the more times I would have to use this to come up with the future value of the sum. And that obviously is going to get very awkward if I keep increasing the compounding frequency. So instead, for these cases, there is an alternative formula we can use. And that's what's going to come up on the next slide. Okay. This alternative version of our future value formula, which is meant for cases when we have interest compounded more than once a year. It's going to save us a lot of time as long as we implement it properly. So this is the motivation for what's coming next. Now, the formula itself contains all variables that we already know except for one thing. Let me just note that right here. Note we will be using N to represent what we call compounding frequency. In other words, for annual compounding, N equals 1. For semi-annual compounding, N equals 2. And that means once per year. This second one means twice per year. Okay, so you can probably guess what's coming next. All right, so if annual means N equals 1, if semi-annual, N equals 2, that implies that with quarterly, N equals 4, and monthly compounding, N equals 12, and then finally for daily compounding, N is 365. Okay, so from now on, when you see that letter N, it tells me how many times a year the interest is being paid, or compounded as it's called. With that in place, every term in that formula is already known to us. It's just that it's a little messy. All right, so finally, why don't we go ahead and introduce this amazingly important formula, and here it is. Now you can see there's a lot of parts to it. It's not that scary, but we have to be very careful with it. Now, what I would like to do with it is go back and double check the results we had in our example, where we had interest compounded twice a year and 4 times a year. You can see you recognize all those terms. Not one of them is new, except for the N, which we now know what it means. And so we should have no trouble, but again, we have to be super careful with it. All right, so I'm going to sneak that in here. Let me give you a minute. We're going to go back and use this amazing formula to double check our results from earlier. Now, one of the reasons why this is so complicated is because you've got a ratio inside the parentheses and a product in this exponent. So yeah, it could get messy. Now, for that reason, what we often would like to do is maybe simplify the formula before we actually use it. And you'll see what I mean in a minute. So let's go back and revisit this example. An investor puts $1,000 in the bank, or a bank, for 1 year when the interest is 4%. What is the future value of this sum? In other words, what will be the balance at the end of the year under the following assumptions? Okay, so we're going to do this for 3 times actually. We're going to see how this formula works when N equals 1, semi-annual compounding, And finally, quarterly. We only did those 3 cases. All right, so what I'd like to do is take that new formula and recalculate all these 3 and double check and compare them to what we found earlier. And if we do it correctly, of course, we should get the same results. All right, so let's start with the first case. Now, once again, I'll copy the amounts on top for you. Or actually, I'll do it like this. All right, so remember that this was $1,000 with a 4% rate and time is 1. Now the formula, once again, is A equals P times 1 plus R over N to the NT power. In the first case, when the compounding frequency is 1, let's try this. A equals 1,000 times 1 plus 0.04 over 1 raised to the 1 times 1 power. So this one is especially easy because all we have here is actually 1.04. The exponent here is 1. So this one is especially simple. Whoops, what did I do? Sorry. It's 110 to 40 even. So that's, but of course you would expect that with the annual compounding. It's really simple. And this is exactly what we had earlier. All right, now let's try this again for n equals 2. Now this time it's going to get a little more challenging. Okay, so you know what, actually, let me do this. All right, so this way I don't have to rewrite everything every time. So now n equals 2. Actually, we can get rid of all of this. All right, so if n equals 2, and we have to change this too. Part B, n equals 2. So now what happens? 1,000 times 1 plus 0.04 over 2. And we have then an exponent 2 times 1. So you actually have here 1 plus 2%. And here you have the exponent is 2. So on your calculator, you should do this. Now, this is where it gets a little tricky. In fact, what I'm going to recommend that you do is do this not in this order that you're seeing here. I would like you to go from right to left this time. Go 1.02. And then you can use your x squared button in this particular case. I'm going to do it along with you. Hold on 1 second. I got my calculator here. X squared, and this, but this is very, you can't always count on that being there. So you put 1.02 times x squared, or just square it. And then I think you should multiply by 1,000. So you see what I'm having you do? I'm having you go not from left to right like you normally do. What your strategy is with calculators is often to simply take the most complicated piece and do that first, and then work on the rest of it. If you go from left to right, you'll need more parentheses. And I really think that will make it more complicated. Now, having said that, you don't have to do it this way. I just happen to think it's a good idea. And of course, this is exactly what we had. Remember those 40 extra cents? If you don't want to do it this way, if you go from left to right, you'll need to do this. 1,000 times, open parentheses, so it's 1,000 times, open parentheses, 1.02 squared, close and equals. I don't know. I mean, I kind of like the first. You can do them both. It doesn't matter. If you want to go from left to right, though, you've got to make sure that this expression, 1.02 squared, is in parentheses. Now, when we get to our more complicated formulas, again, you may want to do it piece by piece. Either way, you're going to get the same answer. All right, let's make sure we've all got the right answer. And of course, that's what we had when we did it the long way earlier. 1,040.40, that extra 40 cents is our compound interest. Now let's try it with quarterly. All right, I'm just going to steal this one. So we're going to change this to quarterly, just to confirm what we had earlier. Okay, so what we were doing here is then 1,000 times 1 plus 0.04 over 4 to the 4 times 1 power, which can be reduced to 1,000. This is actually 1 plus 1%, and the exponent is 4. So again, there's a couple of ways of doing this. You can do 1.01 to the 4th power. Now remember, because there's no x to the 4th key, what you have to do is use x to the y. Okay, so it's 1.01 exponent 4 equals, hold on one second. Times 1,000 equals, and you will in fact get what we had earlier, which is 1,040.604. The other option is to go from left to right, which means 1,000 times, open parentheses, 1.01, x to the y, 4, and the close equals. That should do it. Let's see. Let me double check that. Yeah, either way, you'll get the same thing. So you can decide how to approach this. All right, now I'm going to throw a challenge your way here. I'm going to leave this here so you can see it. But why don't we take this to the next step? And why don't you try n equals 12 and see what you can come up with. So I'm leaving all these steps here so you can follow them if you want to. And what you're going to do is change the compounding frequency to n equals 12 and see what you can come up with. Hmm. Wow, it's a little challenging, isn't it? One thing you do know for a fact is that it has to be more than 1040.604, because as we keep increasing the frequency, as you know, the future value rather has to go up because the compound interest is going up. So if you get less than that, then something's wrong. Oops. Okay, let's see. What have we got here? All right, so I'm going to recycle this one. All right, so for part D, we're going to have n equals 12. So we've got A equals 1,000 times 1 plus 0.04 over 12. All right, now 0.04 over 12, unfortunately, is not an even value. It's a repeating decimal. So you've got a couple of options here. You could try to reduce it to something like, for example, 0.04 over 12 is actually 0.03333. What you could do is replace this with 00 and then a string of threes, let's say 4 of them. That should probably take care of it because, the interest will be rounded to dollars and cents anyway. So depending on what you want to do here, you could put 1.003333 raised to the 12th equals, and then times 1,000 equals. That should take care of it. Let me just double check that on my calculator. 1.003333 raised to the 12th power times 1,000. That's going to give us about 1040. Let's say we'll round it to 74 cents. How about that? So, or else what you could have done is, if you want to go from left to right, 1000 times open paren 1.003333 raised to the 12th power, close equals, that should take care of it as well. 1000 times open parentheses 1.003333 raised to the 12th power, close parentheses, equals, yeah, that's the same. And as we predicted, the compound interest went up another 14 cents roughly because of the compounding frequency. So every time we keep increasing our compounding frequency, we should expect to see the future value going up, and that's because the compound interest is going up. All right, so now all of these details are in the slides already. There's a slightly more detailed discussion in the slides that you can look at. Now, what we need to consider, well, you know what, I'll tell you what, I think that's enough for now. This is a very complicated topic. There's more to come, but I think we got the gist of it. And now next time, what I think we should probably do is practice with this even more, because as you can see, it's a very complicated thing to do. So maybe what we'll do is we'll start next time with a bunch of practice problems. And then when we're really good at this, we can carry on and continue to analyze what this is all about. And then we'll move on to some other related topics. Yeah, that sounds like a good idea. Okay, so let's stop right there. Yes, I know this is a very complicated, especially for first thing on a Monday morning, very complicated. So why don't we just leave it right here? And plus, you've got to finish your midterms anyway in many cases. So we'll just stop here, and I'll see you all on Thursday. How about that?
Thank you.
All right. You're welcome. See you later.
Thank you. Have a great day.
Thank you. Bye.
Bye.